All right, good morning, everyone. Today we are gonna start enjoying the first steps of finite element methods as we apply it to simple string elements. Okay, so we are gonna look at general steps of the finite element method, specifically to string elements. Some of our objectives today would be to define an element stiffness matrix, define a structure or global stiffness matrix, I'm going to demonstrate actually before we do that, we're gonna derive the stiffness matrix for a spring element. And as soon as we have that, I'm going to demonstrate how to assemble the stiffness matrices into a global stiffness matrix. Also hope to illustrate the concept of direct stiffness methods. To obtain the global stiffness matrix. Is it too small? Would you like me to zoom in a bit? Yes. Anytime, please let me know. Good, more? Yeah. And if time permits, we want to apply different kinds of boundary conditions to solve the equations. So one of the first steps in the finite element method is to select an element. And we are going to start simple, because if we understand the concepts on a simple element and use that for illustration, it will be easier to expand into more involved elements as we move forward. So I'm going to start by looking at a spring element. In its simplest form, a spring element extends between two nodes, node 1 and node 2. And the spring has a stiffness K. And it could have a length L. And please remember that when you learned about springs, we learned that the force is directly proportional to the deformation via that spring stiffness K. So this spring could be subject to forces and is going to deform accordingly. When I'm looking at the spring as an element isolated, I can also show element forces applied at the nodes. So node 1, and clearly here we're going to call the direction of this spring the x direction. We're going to have element forces applied on node 1 and node 2 in the x direction. And I'm going to call this force 1. And I'm going to call this force 2. As a result, when the spring deforms, node 1 is going to see a displacement in the direction x, which we're going to call u1. And node 2 is going to see a displacement in the direction x that we're going to call u2. We can. But as we look at it, I think for something simple like this, we see that we only have one direction, the x direction, right? So now we can define, or we have defined an element. And the first thing we want to do here is to define an element stiffness matrix. And an element stiffness matrix would simply relate the element forces F. I'm going to express it first in matrix form. We relate F, the element forces, to the element displacements that we're going to call U. Sorry. So I want to relate these two together. And these two are also directly related via that element stiffness matrix lowercase k. Now, so far, I have defined F, I have defined U, and we are yet to evaluate the element stiffness matrix. So I can come and expand and say this F is F1 and F2, a column matrix of the element nodal forces. And U is a column matrix of the displacements. And maybe I can call this D, that would have a U1 and a U2. So I still am yet to evaluate that stiffness matrix K that relates F to D, where F is a 2x1, D is a 2x1, and clearly this K is going to have to be a 2x2. So we can say that this K is the element, or this, element stiffness matrix for the spring element. K, and please note I'm using lowercase k, relates nodal displacements D to element nodal forces F. And maybe we can say relates element nodal displacements as well, to be more precise. Element nodal displacements D to element nodal forces. So we want to start looking at derivation of K for a spring element. And for that, we're going to use our prior knowledge. I'm going to take this spring and load it in tension. So you see here, the spring is loaded in tension. Now, as a result of loading the spring in tension, we are going to get an elongation, right? So spring is loaded in tension. It elongates delta, where delta would be equal to, this is U2 and this is U1. Delta would be equal to U2 minus U1. for a spring, with a spring constant K, we can relate T to delta via that spring constant. So we can say T is equal to K times delta. Where T is the tensile force and delta is the total deformation. Which is the same as elongation. If delta is equal to U2 minus U1, we can then say that T is equal to K multiplied by U2 minus U1. Now for the spring elements that we defined here, I want you to start relating these two diagrams. What is this F1 equal to here? You can say that this F1 is equal to a minus T, and this F2 is equal to a T. If F1 is equal to minus T, I can say that F1 is equal to, I will just change the order here, and we'll write it as K multiplied by U1 minus U2. And for F2, I would say F2 is equal to K times U2 minus U1.
Yeah.
I hope you're all able to make the relation between these figures. Okay. So now I have here two equations. That we can express the above element force equations in matrix form. This would be F1, F2 as they relate to U1, U2. For the first equation, I have a U1 times K minus a U2. Oops, sorry. This is a K. So K times U1 minus a K times U2. For the second equation, I have a minus K U1 plus a K U2. Therefore, the stiffness matrix for a linear spring element K is equal to K minus K minus K and K. This K is referred to as the local stiffness matrix of the element. And what does local here imply? When I defined my element, and this goes back to the x direction, I identified the x direction in the same direction as the spring to make things easy. So this x becomes specific to that element, because when I have a structure, it's not necessary that all the springs are going to be in the horizontal direction. So this is the reason we call it a local stiffness matrix. Now, this K is a square 2 by 2 symmetric. See the diagonal, and I have minus K and minus K. So it's a square symmetric matrix. And it is singular. A singular matrix, meaning we cannot find an inverse. So here we use the basic process to derive the stiffness matrix for a spring element. Anyone still writing? Good. So we defined an element stiffness matrix, and we drove the stiffness matrix for a spring element. I still want to define a structure or global stiffness matrix and demonstrate how to assemble it. Now we understand that there are local directions and global directions. But to keep things simple for now, I'm going to make up a simple structure that is comprised of more than one element. And I'm going to keep all the elements in the same direction, so we don't have to worry about going from local to global. But keep in mind, this is one of the reasons we call it global or a structure stiffness element. It has to be expressed with reference to one direction that we call the global direction. Okay, so for now, we're going to keep it simple. And let's say I have a structure that is made of an assembly of two springs. Now, both of them are oriented here in the X direction. Now, this structure is going to be subject to forces, whether knowns or unknowns. These could be applied forces or support reactions that I'm going to call here. Let me first identify the nodes. So this is node 1, node 2, and node 3. So I have an element 1 spring element that extends between these two nodes. I'm going to call this element 1, and this is element 2. And the structure as a whole is subject to applied forces. So these are not element forces. I'm going to call it at node 1, it is F1. At node 2, it is F2. And at node 3, I have here F3. And please note that I'm using uppercase Fs. Now, this structure is going to see nodal displacements. At node 1, I'm going to see a U1. At node 2, I'm going to get a U2. And at node 3, I'm going to see a U3. The global stiffness equations are going to relate the column matrix of the uppercase F to the displacement matrix of all the U's for the structure. So these two are going to be related via a global or structure stiffness matrix. And please note I'm using an uppercase K. So this uppercase K is the stiffness matrix of the whole spring assemblage this K relates global coordinates nodal displacements D to global and I'm going to add the word external forces F as shown here. F is equal to K times D, where in this case, F, would be equal to F1, F2, and F3. And D is equal to U1, U2, and U3. So as you can see, this is a 3 by 1. This is a 3 by 1. So we expect K to be a 3 by 3. What I'm going to do next is I'm going to look at each element separately. So I'm going to take this first element 1. And second element 2. So element 1 extends between node 1 and node 2. And element 2, so this is element 1. And element 2 extends between node 2 and node 3. Element 1 has a spring constant K1, and element 2 has a spring constant K2. I should have actually shown this here too. Now we've already derived element relationships. So I can come here and look at element 1. Say element 1 has element nodal forces that I'm going to call F1, comma 1. So the second subscript identify that it's applied to element 1. Okay, and you're going to see why. Because now at node 2, I have an F2 to element 1, while the second element also get a force F2 applied to element 2. So you see why we have the second subscript to differentiate between these two nodal element forces. And keep in mind, I'm using lowercase f. I'm going to come here and show my F3 element 2. And everything still is in the x direction. So my global is the same as my local for the two elements to make things simple. Now, element 1 is going to see displacements at node 1, U1, which, by the way, is the same as this U1. Right? But this F11, the red, is not the same as this black F1. Actually, it can be, but it does not have to be, right? There could be other elements connected, as we're going to see here. We have two F2s and only one F2 in black. So I'm going to also show the displacements here. This U2 is the same as this U2. And here we have U3. Now I can write the element equations for each of these elements based on what we just derived. So based on what we just did, these are element equations. So I can write these equations for my first element, basically F11, F21 is equal to K1 minus K1 minus K1, K1 multiplied by U1, U2. I can do the same for the second element. I have here F22 and F32. These are the element nodal forces, are equal to K2 minus K2 minus K2 and K2 multiplied by U2 and U3. Now as I isolated the elements and was able to write element stiffness equations, I also want to look at the forces applied to the nodes independently. Question? No, lowercase. These are element equations, like the ones we just derived. So if I look at node 1, node 1 is subject to an external force, F1, and we have a force from the node acting on element 1. So if I look at the internal equilibrium, there must be the opposite of this force acting on node 1. Likewise, if I look here at node 2, now node 2 is subject to this external force F2 and F22 opposite and equal, as well as F21 opposite and equal. Likewise, if I go to node 3, I have an external force, F3, and I have the element nodal force. I'm going to show the opposite and equal. I have F32. So what do we get from the equilibrium of these nodes? I can get 3 equations, namely F1 is equal to F11 from the equilibrium, right? And F2 here is equal to F21, and I'm sorry, I did a mistake here in the direction. They're both going in the positive x direction, so these should all be going in the negative. Okay, so that would tell me that this F2 is equal to F21 plus F22, and F3 has to be equal to F32. Right? Question?
So if at F2, if they are both going to the same direction?
At node 2?
Yes,
they're both going in the same direction, which is the negative x direction.
So what counters the other spring, because we have 2 springs there?
These are the nodes. I'm looking at the node 2.
Okay.
So I'm looking at the equilibrium of the node.
Okay.
So at the node, I'm showing the external force. And at the same time, the element nodal forces are acting on the nodes in the opposite direction.
So you can say F21, F22 is countering F2.
Correct. But in order for the node to be in equilibrium, the 2 red combined has to be equal to the black.
Okay.
Right? Now what? We have equations for all the red forces. So let's substitute in these equations. Okay. So for F11, I would say this is equal to K1 U1 minus K1 U2. Correct? For F2, I'm going to take F21, which is equal to minus K1 U1 plus K1 U2, and then plus F22. And what's F22? F22 is K2 U2 minus K2 U3. For F3, I do not have anything multiplied. I have F3 too. I don't have anything multiplied by U1. So I'm going to start here, and it goes like minus K2 U2 plus K2 U3. Can I write these equations in matrix form? So we can write that as F1, F2, and F3 equal to this big or global or structure stiffness matrix multiplied by the structure nodal displacements U1, U2, and U3. Okay. So for the first line, I have, let me just make some columns here. So here I have a K1 U1, and I have a minus K1 U2, and I have a 0 for U3. On line 2, this is a K1. For F2, I have a minus K1 U1. I have a plus K1 U2. And I also have a K2 times U2. So within this column, for element 2, 2, I'm going to add a plus K2 U2. And then I have a minus K2 times U3. On the third row, for F3, I don't have anything multiplied by U1, so I'm going to put a 0. And for the second column, I have a minus K2 times, these are 2's, minus K2 times U2. So I'm going to get a minus K2 U2. And then I have a K2 times U3.
The second row first column, is that supposed to be K1 or K2?
K1, thank you. And I hope you're seeing where it's coming from. Minus K1 here. So we were able to write the global stiffness equations or assemble the element matrices to form the global or the structure stiffness matrix K. And before we move on, let's look at a few things here. If we look carefully, we will see that we still had the element stiffness matrix for element 1 and the element stiffness matrix for element 2. We really superimpose them together such that each element is going in the row and column that correspond to the force and displacement that are being related together. For example, if I look at element 2, 2 in this 3 by 3 matrix, it included element 2, 2 from the first set of element stiffness equations that relates the force 2 to displacement 2, as well as element 1, 2 from the second set of equations, because it relates an element nodal force 2 to displacement U2. So these two got superimposed together or added together in this cell. Now, of course, this was nice and easy because I'm only looking at 2 elements. So this is simple process. But we want to expand that so that it's easy to apply for more complex structures. And this is what I want to illustrate next in using the direct stiffness method to assemble a global stiffness equation. Before we get into that, let's here just conclude that this uppercase K is equal to K1 minus K1, 0, minus K1, K1 plus K2, minus K2, 0, minus K2, and minus K2 is the global, the structure or whole structure stiffness matrix. K, of course, this is a 3 by 3, is a square symmetric matrix that is singular. So you see here the diagonal. The diagonal elements of K are always going to be positive. K relates the uppercase F's, or D relates D, the nodal displacements, to the global external forces F. And I want to say a quick note on D, because I use the same D for the global or the structure equations as well as the local. So please keep in mind that U2 for element 1 is the same as U2 for element 2. So we simply call it U2. And what we're saying here is elements 1 and 2 must remain connected at the common node 2. This is called continuity or compatibility requirement. Compatibility requirement. Sorry. compatibility requirement. This is an I. I think I didn't say that, but F is, I think we said that, global nodal forces, right? F is the global nodal forces. D is the global nodal displacement. And of course, again, here, global is the same as the local. And K is the total or global or system stiffness matrix. We can refer to these sets of equations as the equilibrium nodal equations. Next, let's use the direct stiffness method. For uppercase K. So I'm gonna go use the same assemblage here of these two springs. Node 1, node 2, and node 3. This is K1, this is K2, this is element 1, and this is element 2. This is the X direction. And now we know that for element 1, I can express my stiffness matrix K1 as equal to K1 minus K1 minus K1 and K1. And for element 2, K2 is equal to K2 minus K2 minus K2 and K2. And I'm going to identify for each of these element stiffness matrices the displacement that relates to each row and column. So I will come here and say this stiffness matrix K1, the first row is multiplied by U1. So that's the degree of freedom that is associated with the first row. And for the second row, I have a U2. I'm going to do the same. Here is U2 and here is U3. So I'm just labeling the row for each of these element stiffness matrices according to its degree of freedom. Okay, corresponding to row 1, I have column 1, and I'm going to also relate column 1 to U1 and column 2 to U2. Likewise here, this is related to U2 and U3. And we're going to understand why. So now here I'm looking at each of these element stiffness matrices. Both of them are a 2 by 2. And when I'm looking at the entire structure, I have 3 degrees of freedom, U1, U2, U3. So we understand, based on the number of degrees or the global degrees of freedom, the global stiffness matrix K is going to be a 3 by 3. In the direct stiffness method, I'm going to say here that in order
And then looking, how do you know these are the number of degrees of freedom?
Good. When I defined my elements, good question. When I defined my element, my spring element, I defined it as a 2-node element, and each node has only 1 degree of freedom. Now, this is given that I'm working only along the x-axis. If I'm working in plane, it will have 2 components, an x component and a y component. And we're going to get into that in the next chapter, following chapter. But for now, let's keep it simple as uniaxial. Good. So in order for us to superimpose the element matrices we must expand them to an order size of the total structure and I should say here element stiffness matrices, just to be clear. And here will be the total structure stiffness matrix K. So how are we going to do that? We simply add rows and columns of zeros for the displacements that are not associated with that particular element. And I'm going to demonstrate here. So my expanded stiffness matrices are going to become K1, and we can call them like prime for expanded. I want to make this a 3 by 3, and this lowercase k is going to be equal to, and I'm going to make it a 3 by 3. So I want this to be a 3 by 3, where the first row is going to associate it with displacement or degree of freedom 1, 2, and 3. Likewise for the columns, I'm going to have U1, U2, and U3. Now clearly, element 1 extends between node 1 and node 2 and is related to displacements 1 and 2, but not to displacement 3. So what we're going to do here is we are going to fill in zeros corresponding to the third displacement, or U3. Then I'm going to simply copy the elements from my element stiffness matrix K1. So I'm going to come here and still have minus K1, K1, sorry, this is a plus, this is a minus. Sorry, I messed this up. Minus and plus. Okay. Likewise for K2 prime. So I'm going to come here and write my K2 prime as a 3 by 3 is equal to. So we have a U1, a U2, and a U3. U1, U2, and U3. So I'm going to look at element 2. And element 2 extends between node 2 and node 3. So clearly, the first degree of freedom is not associated with element 2. So I'm going to come here for the first degree of freedom, and I'm going to put zeros on the first row corresponding to U1, and zeros on the first row corresponding to degree 1. Then I'm going to fill in using the elements from the stiffness matrix of element 2. So I'm going to have a K2 minus K2 minus K2 and a K2. Now, if you're wondering how we're going to relate these expanded element stiffness matrices to element nodal forces and element nodal displacements, I can simply write it as F11, F21, and 0 is equal to this K1 prime multiplied by U1, U2, and U3. And likewise, actually 0 here, and then F2, 2, and F3, 2 is equal to this K2 prime, which, by the way, this is a 3 by 3, and this is a 3 by 3, multiplied by U1, U2, and U3. Now I can write the equilibrium nodal equations as F1, F2, F3 is equal to F11, F21, and a 0 plus 0, F22, and F32. These are the ones we had here. Can you see the correlation? From the compatibility we have all these, this U1 is the same as this U1. So if I come here and say, oh, this is U1 of element 1, element 1, element 1, and this is 2, 2, and 2, I can, from compatibility, we can say that this U1, and of course, there is really no U1 associated with element 2, but specifically here to U2, I can say that U2 element 1 is the same as U2 element 2, and we're just going to call it U2. And I can apply that to any of the others, like U3 1 equal to U3 2 equal to simply U3, and so on. So now I can expand this and say that F1, F2, F3, I'm going to take these two as common factors, right? So I can say, write it here, this is equal to K1 prime, the 3 by 3, multiplied by U1, U2, U3, plus, sorry, go ahead.
U3 1 is U3 1.
U3 element 1
Yeah.
and U3 element 2.
Okay.
We're going to just call it U3 because compatibility. These nodes, if I'm referring to node 3, even though it's not associated with the element, but we're going to refer to one displacement for node 3 to keep the structure intact. Okay. So I have here K2 prime, which is the 3 by 3, multiplied by U1, U2, and U3. So I can write it as F1, F2, F3 is equal to, if I take the displacement matrix as a common factor, I will have here this 3 by 3 matrix that is made by adding K1 prime to K2 prime, or superimposing the element stiffness, oops, that's a problem, matrices expressed in the same order as the global stiffness matrix K. Now, how would I do that? I already have the expanded form, right? So if I take these two and add them together, I would get F1, F2, and F3 equal to U1, U2, and U3. And if I add these two matrices together, by adding the corresponding elements, I will get a K1, a minus K1, and a 0. I will get a minus K1, K1, and if we look here carefully, I have a K1, and I have here a K2. So I will get a K1 plus K2. I can use a different color here. And then for element 2, 3, I have a 0 and I have a minus K2. For 1, 3, I have a 0. I'm sorry, for 3, 1. But for 3, 2, I have a minus K2 coming from K2. And here I have a K2. Which, of course, if you compare to what we did earlier, you will find that the direct method gave us the same results. So the expanded element matrices could be added directly to obtain the total stiffness matrix. Expanded element matrices could be added directly to obtain the total stiffness matrix of the structure. I just have to mention one thing here that I want you to keep in mind. For this simple problem, because the global and local axis are the same, it's simply the expansion was simple, just adding zeros. In general, I would need to transform the element stiffness matrix before I expand it. So then everything is in terms of the global directions. We're going to save this step for a later chapter, but just keep it in mind. Now, this direct stiffness method is reliable.
Does this apply for more than 1 degree of freedom, or would that have to be added separately?
Oh, absolutely, it will apply. Okay, so this direct stiffness method is reliable method specifically to problems with large number of degrees of freedom. And this is something important to keep in mind. And I'm going to even add, so this direct stiffness method is reliable and applicable to problems with large numbers of degrees of freedom and we can avoid the expansion of each element stiffness matrix, okay, simply by labeling the rows and columns. So what you're going to do if you're using a computer program, you label the rows and columns of each element stiffness matrix K according to the degree of freedom associated with them. What does that mean? If I come here to this problem, and instead of having to expand the stiffness matrix, I would label the row and column according to the degree of freedom associated with it. And then when I'm doing the superimposing, I don't have to worry about all the zeros like we did here. Like when we did here, when I was adding, I had a bunch of zeros that really did not affect the answer. So what I will be doing is I'll be taking like this portion from K1, and I know where this is going to go in the global stiffness matrix. And I will take this portion from K2 and know where it goes. And everywhere else, I'm simply going to put zeros. So uppercase K is constructed. I'm going to finish straight away. By directly adding the terms associated
We can see.
with a degree of freedom into corresponding identical degree of freedom location in the total or global stiffness matrix K. So today we have derived the element stiffness matrix for a spring element. We've learned how to assemble the global stiffness matrix. And on Thursday, remember this global stiffness matrix is a singular matrix. So in Thursday, we're going to learn about the boundary conditions and how we apply them to solve the equations for the unknowns. And we're going to do example of that. Okay, I'll see you all on Thursday. Thank you. You want the last part?
We get some.